On this question, we want to use the graph to find the limit. And the limit we're trying to find is the limit as x approaches -6 from below of the function that we see in the graph. So as I look at this limit, and I want to use the graph, this portion is going to tell me the part of the graph that will give me the answer to my question. So this is saying x is approaching -6, so I want to go to where x equals -6. And then this symbol here is x approaching -6 from below. And that means I want to use the numbers that are less than -6 in order to answer the question. So I want to match this with the graph. So I've got the y value at -6, and then this portion of the graph has x values that are below -6. So when I find the limit, I want to find the limit as x is approaching -6. So I'm going to trace the graph going in this direction because this is going to get me closer to an x value of -6. And as I trace the graph, I'm arriving at this y value here, which is 6. So the limit as x approaches -6 from below is 6. On this question, we want to use the graph to answer this limit question. On this one, we're finding the limit as x approaches infinity of f of x. So this part under the limit is going to tell me which portion of the graph to use. X approaches infinity is going to use this part of x approaching infinity indicates this part of the real number line, and then we're going to use the portion of the graph that matches that. We want to trace towards infinity, so we're going to trace going in this direction because there my x is getting larger and larger. Now in this graph, we've got a dashed line here, which indicates that we have a horizontal asymptote. So this line is going to get closer and closer to the y value here that is marked by the horizontal asymptote without ever reaching it. So this limit is approaching that y value of 2. So on this question, we want to use the graph to answer this limit question. We want to find the limit as x approaches -infinity of f of x. X approaching -infinity tells me which portion of the graph to use. So I'm going to look at the x-axis as my real number line and think about the portion of the x-axis that's being described. X approaching -infinity. So -infinity is the idea of it going on forever in the negative direction. And so I'm going to look at the furthest left part of this graph to find x approaching -infinity. And x approaching -infinity needs to go this way to approach -infinity. So I want to find the portion of the graph that is matching that description. So I'm going to find the farthest left portion of the graph, which is right here. And I'm going to trace away from 0 because that's approaching -infinity. And think about what's happening to the y value here. What's happening to the y value is it's going to continue to go down and down and down and down. And so that means that our y is approaching -infinity. So we have the limit as x approaches -infinity of our function being -infinity. On this question, we want to use the graph to find the limit x approaches 0 from above of f of x. And this picture is our f of x. X approaches 0 from above is going to tell us which portion of the graph to use to answer this question. So we have an x value of 0 here, and the values of x that are above 0 are to the right of 0. So I'm going to use the part of this graph that's to the right. If I want x to approach 0, I would need to travel towards 0 along the line, and that would be in this direction. So as I trace, I find myself leading towards this y value here, which is a y value of -1. So I have the limit as x approaches 0 from above of f of x being -1. On this question, we want to use the graph to find the limit. The limit as x approaches -2 of f of x. And this graph is the graph of f of x. So the limit that we're looking for is the limit as x approaches -2 of f of x. X approaching -2 is going to describe what portion of the graph to use. So we have an x value of -2 here, and if you'll notice that there's no specification right here telling me to look at the limit from below or look at the limit from above. So when we don't have a specification, we need to look at the limit coming from either side. So we need to look at the limit from below as well as the limit from above. So I'm using the portion of the graph that's to the left of -1 for below, and the portion of the graph that's to the right of -2 from above. We want to trace going towards an x of -2. So from below, we're tracing this way, going towards an x of -2. And on the right, or above, we're tracing this way, which goes towards an x of -2. Now, when I'm looking at this portion from below, my y value is approaching this spot right here, and that's a y value of 0. So this right here is telling me that the limit as x approaches -2 from below of f of x equals 0. And then from above, the limit as x approaches -2 from above would be approaching this spot right here. The graph is leading towards this spot, and that has a y value of 3. So that limit from above is 3. And you can see that these limits are not agreeing with each other. In order for this limit that we're looking for to exist, it has to approach the same value on both sides. So since we're approaching different values on each side, this limit does not exist. On this question, we want to find the limit as x approaches 2 of f of x using the graph. So we're going to find the limit as x approaches 2 of f of x. So x approaching 2 is going to describe which portion of the graph to use. So we have an x value of 2 right here. This limit doesn't specify to approach 2 from below or above, so we need to approach coming from both directions. So I want to approach 2 from below, and I would trace going towards an x value of 2, and I want to approach 2 from above, and I want to approach 2 going towards 2. So that means that I'm going to use this portion of the graph to approach 2 from below because it matches what I've got here on the x, and I want to use this portion of the graph to approach 2 from above because it matches this portion of the x-axis. I want to trace the graph going towards an x value of 2, so I'm going to trace this way from below and approach this way from above. As you can see, as I'm tracing the graph, I'm approaching the same y value from both sides. I'm approaching this spot right here on both sides of the graph, and that's a y value of 0. So this limit as x approaches 2 of f of x is 0. Okay, on this question, we want to find the derivative of y equals x over square root x squared plus 1. So when you look at this equation, you want to decide which derivative shortcuts you're going to use. So the first thing I notice is the fraction bar, and so I'm going to use the quotient rule. The quotient rule is this here, taking the derivative of a fraction. And when you calculate the derivative of a fraction, you're going to do the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And then when I look at the numerator and the denominator individually, the numerator is just x, and the derivative of that is easy to calculate. And when I look at the denominator, that looks a bit more complicated. So I want to think about that a little bit more. Having that radical can make it a little bit messy, so I can use algebra to rewrite this as x squared plus 1 to the 1/2 power. And now that it's in that format, I can see that I'm going to use the chain rule to calculate the derivative of that portion. Or you can think of it as the general power rule. So if you think of it as the chain rule, it looks like this. You have an inside function and an outside function, or a composition, f of g of x. When you have the derivative of a composition, you're going to calculate it this way. You take the derivative of the outside function, you leave the inside function alone, and you're going to chain by multiplying by the derivative of the inside. So that is your chain rule, which we can use when we calculate the derivative of the denominator. Or you might recognize that the denominator fits the pattern of the general power rule. And the general power rule looks like this. If you have u to a power and you want to calculate the derivative of that, that would be n times u to the n minus 1 times u prime. So this is a combination of the power rule and the chain rule together, and it's called the general power rule. So this is what we're going to use in order to calculate this derivative. We need to start with the quotient rule because we're only going to be using the chain rule on just the denominator, so you don't want to start with the chain rule because you're only doing the derivative on that one part. And I want to correct this up here with the quotient rule. We should have g squared in the denominator, the bottom squared. Thank you for that. So we're going to use the quotient rule to calculate this derivative. So we're going to do the bottom, that's x squared plus 1 to the 1/2 times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So we have x squared plus 1 to the 1/2 power times the derivative of x minus x times the derivative of x squared plus 1 to the 1/2 power over x squared plus 1 to the 1/2 power squared. So now I need to calculate these derivatives. To continue, I'm going to copy down x squared plus 1 to the 1/2 power. The derivative of x is 1. And then I'll use the chain rule or the general power rule to calculate the derivative of x squared plus 1 to the 1/2 power. So that would be, I'll bring that power down, leave the inside alone, take 1 away from the power, so that's negative 1/2, and I'm going to chain by multiplying by the derivative of the inside. And this is all over that denominator. We've got x squared plus 1 to the 1/2 power squared. When we multiply those two, the powers become 1. So it's x squared plus 1 to the first power. So at this point, we do have the derivative, but we want to clean up the derivative with some algebra. So I notice I have the 1/2 and the 2 here that will cancel each other out. And both of these terms in the numerator, I'm going to box out the 2 terms. We have one term here and another term here. Both of the terms in the numerator have a common factor of x squared plus 1. So I'm going to factor out that common factor. And when I factor it out, I'll have x squared plus 1. And I'm going to choose the lower power, which is the negative 1/2 power. And if I factor that out of this first term here, this first term, I'm going to be left with x squared plus 1 to the 1/2 minus negative 1/2 power. I'm factoring out that negative 1/2 power, so that's why I'm taking away that power. And then over here, the x squared plus 1 to the negative 1/2 factors out completely. So I'm going to be left with this x and this x multiplied together. That's an x squared. And that's all over our denominator of x squared plus 1. Inside the parentheses, 1/2 minus negative 1/2 is 1. It's x squared plus 1 to the first power minus x squared. This factor right here that has a negative exponent can be moved down to the denominator. X squared plus 1 to the 1/2 power. We have an x squared plus 1 as a factor already there. So in the numerator, I have x squared plus 1 minus x squared, which is going to leave me with just a 1 in the numerator. And in the denominator, I have the same factor being multiplied. I'm going to add the powers together. That's one of our exponent rules. So that becomes x squared plus 1 to the 3/2 power, or square root of x squared plus 1 cubed. So we've got the derivative being 1 over square root of x plus 1 cubed. Thank you for checking out my videos. Have a great day.